Alright, welcome back to the channel. This is the PreCal Chapter 4 practice test. So number 1, find the positive and negative coterminal angle of 13 pi 6. Remember, coterminal means it has the same start and end point. So basically what you're going to do is find another angle that has like one full revolution or two full revolutions or however many full revolutions either forward or backward from the given point. A full revolution is 2 pi. So if we have 13 pi over 6, if I add 2 pi to that, that's really the same as adding 12 pi over 6, which gives me 25 pi over 6. That would be a positive coterminal angle. And then a negative coterminal angle, we just need to go backwards. So we would subtract 2 pi or subtract 12 pi over 6 from the 13 pi over 6. And that leaves us with pi over 6, but that's still positive, and we need a negative angle. So we're going to have to subtract 2 pi again. So we have pi over 6 minus another 12 pi over 6, which gives me negative 11 pi over 6. It's worth pointing out that even though I said 25 pi over 6 was my positive, I could have also said positive pi over 6 was a positive coterminal angle because that angle was also still a positive angle that happened to be coterminal. Alright, part B, find a positive negative coterminal angle for negative 9 pi fourths. So I'm going to do the same thing. I'm going to add 2 pi, which in this case is going to be really 8 pi over 4, and it's going to give me negative pi fourths. That's a coterminal angle, but that's negative, so I'm going to put it down here. And then I'm going to add 2 pi again, which again was 8 pi over 4. I'm going to get 7 pi fourths. So in both cases, we had to worry about not just adding or subtracting one revolution, but we had to make sure we did it enough times to get both a positive and negative number. Number 2, find the complement and supplement of those angles. Remember, complement means they add up to pi halves or 90 degrees, and supplement means they add up to pi or 180 degrees. So if I need a complement of 3 pi fourths, I'm going to do pi halves minus 3 pi fourths, and I'm going to get, once again, get common denominators, so I'm going to get 2 pi fourths, that's negative pi fourths. That would be my complement. However, we discussed in class that a complement needs to be two positive angles. So since 3 pi fourths was already bigger than pi halves, we can just go ahead and say that there is no complement. The supplement, same thing. I'm going to take pi halves. No, not pi halves this time. I'm going to take pi because it's 180 degrees. Pi minus 3 pi fourths. We can get common denominators, or you can just think about it. What's 1 take away 3 fourths? That's going to be left with pi fourths is my supplement. Part B, same idea. For pi 6, I'm going to start with pi halves minus pi 6. Pi halves is 3 pi over 6, so that leaves me with 2 pi over 6. When I reduce that, my complement becomes pi thirds, and then my supplement is pi minus pi 6. Simplify that, and again I'm going to get, I can just think about that logically, and I get 5 pi over 6. Moving on to 3, given that the sine of an angle is 1/2 and the cosine is negative, find all my trig functions. So if sine is a positive value and cosine is a negative value, we have to be in quadrant 2. So I'm going to sketch that triangle real quick in quadrant 2. And I know that cosine is opposite over hypotenuse. So I have, here's my angle. I have 1 and 2. And then using Pythagorean theorem, 2 squared minus 1 squared is the square root of 3 when I take the square root of that. So my cosine is rad 3 over 2. Tangent is 1 over rad 3, which is the same as rad 3 over 3. Cotangent is radical 3 over 1, or just radical 3. Secant is the reciprocal of cosine. So that's going to be 2 over radical 3, which is 2 rad 3 over 3. And then my cosecant is the reciprocal of sine, which is 2. Number 4, find the reference angle. Remember, the reference angle is the quickest way back to the x-axis, always the quickest way back to the x-axis. It's going to be some value between 0 and pi halves, or 0 and 90 degrees. So if we think about where negative 5 pi fourths is, we know that all the pi fourths are the 45s. Negative 5 pi fourths means I'm going to go backwards. So I'm going to go clockwise. So if I start here at the origin at 0, pi fourths would be here in the middle. I'm sorry, negative pi fourths in the middle. Negative pi halves, negative 3 pi fourths, negative pi, negative 5 pi fourths. So my angle is here, and the reference angle is this little guy, which is the quickest way back. Since I was an additional pi fourths beyond the x-axis, that little reference angle right there is just pi fourths. Part B, 7 pi sixths, same idea, I just need to figure out where 7 pi sixths is. 7 pi sixths, if you're looking at your unit circle, it's over here in quadrant 3, and all I care about is that little angle, which is, since this is pi, or 6 pi sixths, then this little angle, this little extra piece, has to be just an extra pi sixth. So my reference angle here is pi over 6. Alright, number 5. The given point is on the terminal side of an angle in standard position. Remember, standard position always starts at the positive x-axis. So it's going to start over on the right-hand side. Find the angle in radians. So if we're looking at the point negative 3, 4, we know that that's left 3, up 4. It's going to put me somewhere around here. So we want to know, so we really want this angle in standard position, this big guy here. But what we're going to have to do is find its reference angle and then do a little bit of work to get the big angle, which won't be too much of an issue because we know if we're in quadrant 2, whatever this little angle is, we just have pi minus that, which gives us the big angle. So if we set this up, we're at negative 3, 4, using Pythagorean theorem, or noticing this Pythagorean triple, this is going to be 5. And we use any one of our ratios to find the angle. So to find this inside angle here, we can go ahead and use the tangent of 4 over, it's tangent theta equals 4 over negative 3. I really shouldn't use tangent twice, but we'll get over it. And then to get the angle by itself, we're going to take the inverse tangent, and the calculator is going to give us a value of about negative 0.927 radians. Well, the problem is negative 0.927 radians is somewhere down here. So we're obviously not at negative 0.927 because that's over here in quadrant 4. But we do know that reference angles are always equal. So this angle up here that's inside this reference angle is positive 0.927. So the angle that we're looking for is pi minus 0.927, which leaves me with an angle of about 2.21 radians, and that's going to be my final solution there. Now the reason why we got this weird angle was because we picked tangent. Remember, tangent has, or I'm sorry, inverse tangent and inverse sine exist in quadrants 1 and 4 naturally on the calculator. So if we want to ensure we got the correct angle, what we would want to do is instead pick something that exists in quadrants 1 and 2, which would be inverse cosine. So if we did inverse cosine of -3/5, it's going to give us the correct radian right away. So if we just pick our value a little bit smarter, or the trig function that we use a little bit smarter, it's going to give us the value that we're looking for right away without having to do this extra work. But regardless, we can get there. Number 6, find the point on the unit circle that corresponds to 37 pi over 3. So all we have to do is figure out where on this unit circle this angle is, and then use that value to find its ordered pair. Okay? If it's on the unit circle, it's going to be one of the values that we've talked about, like 0 or 1, or rad 2 over 2, or rad 3 over 2, or 1/2, or some negative value of any of those. So the first step is to figure out where is 37 pi over 3. Well, we know that every 2 pi we get 1 full revolution. So we can just start subtracting 2 pi, or 6 pi over 3, from 37 pi thirds, or we can see how many 2 pi's we can actually take out of that. So if I'm looking at this, 37 pi over 3 is really 36 pi over 3 plus another pi third. And I picked 36 pi over 3 because I know that this reduces down to 12 pi, which is 4 full revolutions. So this just goes away, and we're left with pi thirds. So pi thirds is right here on my unit circle. And so we have an ordered pair of 1/2 and rad 3 over 2. Alright, moving on to number 7. 2 gears are adjusted so the small gear drives the larger one, as you can see in that picture. If the smaller gear rotates through an angle of 330 degrees, how many degrees will the larger gear rotate? So first of all, we should understand that the large gear rotates less than the small gear. It doesn't have to rotate as much to move the same distance. So what we're going to do is we're going to figure out the actual distance that the big gear or the little gear rotates. And so the big gear is going to have to rotate the same amount, and we just need to find that angle. So all we're going to use for this is our arc length formulas. I'm going to go ahead and label these gears as 1 and 2. So remember that arc length is r times some angle theta, but theta must be in radians. So the first thing I'm going to do is convert this 330 degrees into 11 pi over 6 radians. So now we want to figure out how far did the little gear move. So gear 1 had an arc length of 3.7 times 11 pi over 6, which was a total distance of 21.31 centimeters. So that means that the big gear also rotated that same amount. Because if we started here and the little gear rotates around 330 degrees, which was to be about right there, the big gear has to rotate the exact same distance. Whatever this distance here is, the big one has to rotate the same distance. And all we need to do is figure out what is the angle in radians or in degrees that makes. So we already know the distance that it travels, so we can use our formula S2 equals R theta, solve for the theta. So S2 has to be the same, 21.31 equals 7.2 theta, divided by 7.2, and we get that theta is equal to 2.96 radians, but I want to be in degrees, so remember to convert from radians to degrees. I have x degrees over 2.96 radians is equal to 180 over pi. Do some cross multiplication or whatever method you choose to use. and we get theta is equal to 169.6 degrees. So that's how far the big gear had to rotate. Number 8. Find the values of the other 5 trig functions if the tangent of some angle is 7/2 and the angle has to be between pi and 3 pi halves. This is important because it tells us the signs that we're going to need so we can set the triangle up correctly. So I have my little coordinate plane here. We know that this is 0, pi halves, pi, 3 pi halves. So my angle has to be somewhere in quadrant 3. So if I draw that somewhere around here, there's my triangle, there's my angle. Remember, tangent is opposite over adjacent, so we're going to have 7 and 2. A little more Pythagorean theorem, we're going to get radical 45, which is 49 minus 4, and then the square root of that. So the sign is opposite over adjacent. We're going to rationalize it, so we're going to get 7 rad 45 over 45. Cosine is adjacent over hypotenuse, which is going to be 2 rad 45 over 45. Cosecant is rad 45 over 7. Secant is rad 45 over 2. And cotangent is 2/7. 9 and 10, graph 2 complete periods. I'm going to warn you, these graphs, the pre-made axes really kind of suck, so we're going to do the best we can here. The test is going to be a little bit better, but we're going to do the best we can do right now. So graph 2 complete periods, be sure to label all the axes. We're going to start down here at the bottom. Amplitude, we know the amplitude is that coefficient out front, which is 2/3. My period is my b, it's 2 pi over b, which in this case is 2 pi over 3. My horizontal phase shift, easiest way to find that is to find our starting point. Remember, our starting point with sine and cosine is always at 0, so we take the inside of the parentheses. 3x minus 4 pi equals 0. Solve for x, so 3x is equal to 4 pi. X is equal to 4/3 pi. So my phase shift is 4/3 pi. My vertical shift is the constant either at the beginning or the end, which in this case is 2. And we have pretty much everything we need other than an ending point, which 3x minus 4 pi equals 2 pi. So 3x is equal to 6 pi, so x is equal to 2 pi. So we start at, so one revolution starts at 4/3 pi, ends at 2 pi. Very similar to what we did in class. I'm going to draw a little unit circle here, see if I can figure out my intervals. I got 4/3 pi is my start, 2 pi is my end. And we got to figure out what we need to count by. So the way we figure out how we need to count, we go back to in class. We had a period of 2 pi thirds. We need to break that up into 4 equals pieces. So we take 2 pi over 3, divide that by 4, and we get pi sixth is what I'm counting by. So each of these quadrants need to be pi sixths apart. So 4/3 pi plus pi sixth is 9 pi over 6, plus another pi sixth is 10 pi over 6, and then 11 pi over 6, and then 12 pi over 6, which is 2 pi. I'm just going to go ahead and put 12 pi over 6. So I could go another positive revolution if I wanted to, but I don't have very much room on this particular graph. So instead I'm going to kind of count backwards to get my other one. Again, the actual graph on the test is going to look a lot better than this, but we're going to do what we can. So if I count backwards another full revolution, I have an actual starting point on my graph at 4 pi over 6, and I'm just going to count it by pi 6. So then 5 pi over 6, 6 pi 6, 7 pi 6, 8 pi 6, which is my actual starting point. So I'm going to put a little vertical line there. That's my starting point. 9 pi over 6, 10 pi 6, 11 pi 6, 12 pi 6. So that's going to be 2 full revolutions in there. I know that my graph has been shifted up 2 units, and then it's also the amplitude is also 2/3. So easiest way to do this, if I make my tick marks each equal to 2/3, so I'm going to have 2/3, 4/3, 4/3. I don't know why that keeps disappearing. 2/3, 4/3. Doesn't like what I'm doing apparently. 2/3, 4/3, 6/3, which is actually 2, which is going to be my starting point. And then 2/3 up above that, that's going to be my amplitude. Alright. So the reason why it was important to mark all those little points, and especially these little imaginary lines, this is my new origin right here in the middle. Since it's a sine graph, we know that sine starts at 0. Then it goes the next interval over, we go up to 2/3 in this case, down to 0, negative 2/3, 0, that's 1 full revolution forward, and then I'm going to go 1 revolution backwards. From 0, I go down to negative 2/3, 0, positive 2/3, back to 0, and when I connect these, I get 2 full revolutions. Number 10, 1/2 secant of x minus pi. Remember we discussed in class it's a lot easier to graph the reciprocal, which is y equals 1/2 cosine of x minus pi, and then deal with it from there. The amplitude is 1/2. The period is 2 pi over b, which in this case b is 1, so my period is just 2 pi, which is good news. Horizontal phase shift, I can see it, it's going to be pi units. If I want to double check it, find our starting point again, that's going to be x minus pi equals 0, so x equals pi. There's my starting point, which is my phase shift. While I'm here, my end point, x minus pi equals 2 pi. So x equals 3 pi, that's my end. And then my vertical shift is, no, there is no vertical shift. Alright, so to find our intervals, we know we start at pi, we end at 3 pi. Since my period is the normal 2 pi, we're going to count by pi halves. So this is 3 pi over 2, 2 pi, 5 pi over 2. And again, I'm not going to have enough room to go forward at a full second revolution, so I'm going to count backwards as well. So, let's see. So I'm going to need to go backwards to at least negative pi. So negative pi halves, 0, pi halves, pi, which is my actual starting point on this graph, 3 pi halves, 2 pi, 5 pi halves, 3 pi. And then I'm just going to go ahead and make little tick marks at the top and bottom for 1/2 and negative 1/2. We can put those wherever we want. Alright, so we're going to start by graphing the cosine function. Cosine starts at the top. So at my new y-axis, I have point there. So at pi, I'm at 1/2. Then I drop down to 0, negative 1/2, back up to 0, and back up to 1/2. That's 1 full revolution. And then on the other side, 0, negative 1/2, 0, positive 1/2. So there's my second full revolution. That's not the graph we want, though. We want the secant of that. So remember, we need to have vertical asymptotes at all of our zeros. So every place where it crosses the x-axis, we should have a vertical asymptote. And then our graph that we care about, we'll make that green. It's going to be these little parabolas from each of those max or min values going towards those asymptotes. And then what we could do if we wanted to, we can actually erase the other function, or if you drew it as dotted lines, that'd be even better. But that would be 2 full revolutions of 1/2 secant of x minus pi. Alright, number 11, construct the function from the given graph, and it tells you it's a cosine of bx minus c. So the fact that we know it's cosine is very helpful. A is half the total height, so if I have a maximum at 2, a minimum at -2, my a value has to be 2. There's a total height of 4. Let's see. There's a couple ways we can look at this. We know that cosine is supposed to start at the top. Easiest thing to do, here's my closest top part. So my horizontal shift is that distance right there, and it's shifting backwards. Looks like if this is 2 pi, then this would have to be 1 pi, so this is half, and this is 3/2. So we're shifting it back 3 pi over 2. And then the other thing we need is a full period. So my next, I just count any full period, it doesn't matter. We could go from the top here to the next top, or I can go from 0 to the next time it hits 0 on a full revolution, which is here. So it looks like my period is 6 pi. Those two things are going to be very helpful for finding this bx minus c. So let's start with the b. We know that the period is 2 pi over b, and that was equal to 6 pi. So if we solve for b, I get 2 pi over 6 pi equals b, so b has to be 1/3. There's my b value. So I have a, I have b is 1/3. The only thing I need to find is c. If I plug in what I know, y equals 2 times 1/3 b, oh, not 1/3 b, 1/3 x, minus c. It'd help if I wrote the entire function. Let's try that again. 2 cosine of 1/3 x minus c. I need to find that c value. Well, I know where my graph started. I have a known value on my graph. I know that this whole thing is supposed to equal 0 when I plug in a -3 pi halves. That's like my original 0 spot. So we're just working backward. Think about like finding the phase shift, how we set whatever's inside of here equal to 0 and we solve it. Well, if it's set equal to 0, I get -3 pi halves. So I'm going to plug the -3 pi halves in for my x. So I've got 1/3 times -3 pi halves minus c equals 0. Those 3's are going to cancel. I get -1/2 pi is equal to, if I move the c over to that side, -1/2 pi is equal to c. So I plug everything in, and I'm going to get, plug in for a, b, and c, I get y equals 2 cosine of 1/3 x minus a -1/2. So that's going to be plus positive 1/2 pi, or positive pi over 2, and that's my function. There's other variations you could do. You could have seen this as an upside down cosine graph that was shifted. Many things you could have done with it, but this is the way we did it was probably the quickest way, the most visible approach. 12, find an expression that satisfies the given conditions. The sine of the arc cosine of x squared over 4 minus x squared, where x is greater than 0. draw a triangle in quadrant 1. So we did some of these in class. Remember, arc cosine means find the angle whose ratio of sides is this, and then find the sine of that angle. So basically all we need to do is set up a triangle similar to the way we did earlier. In quadrant 1, we know that cosine is adjacent over hypotenuse. So that's x squared, and this is 4 minus x squared. And to find this missing side, we're going to have to use Pythagorean theorem. So we're going to have 4 minus x squared, quantity squared, minus x squared is equal to y squared. If I expand everything out, I get 16 minus 8x squared plus x to the fourth minus x to the fourth equals y squared. Those cancel. 16 minus 8x squared is equal to y squared. If we take the square root of that, I get is equal to y. So my y value over here on the side is the square root of 16 minus 8x squared. There's really nothing I can do to simplify that. So we're going to leave that just the way it is. So now I want the sine of that triangle. And sine is opposite over hypotenuse. So we have a ratio of the square root of 16 minus 8x squared all over 4 minus x squared. And that is as reduced as we can get it. So that's all done. 13. Find the height of a tree if a surveyor is 50 feet from the base and the tree measures angles and measures the angle of elevation to the top of the tree is 71.5. So they give us a picture. They even drew the triangle for us. Height is going to be the opposite side. We already know the adjacent side, so we're just going to set up a tangent. So the tangent of 71.5 degrees is equal to h over 50. So 50 tangent of 71.5 degrees is equal to h. Make sure your calculator is either in degrees or use the degree symbol if you're using the Inspire. And you're going to get h is equal to 149.4 feet. Angles, I want you to go to 1 decimal place. Measurements, I want you to go to 1 decimal place. Radians, I want you to go out to at least 3. 14. Very similar problem. You guys can read it on your own. We see the triangle already set up. It's another tangent problem. So tangent of 35 degrees is equal to c over 200. So 200 tangent 35 degrees is equal to c. So the cloud ceiling is 140 meters above the ground. 15. The height of the tree below is 51 feet. And the man is standing 68 feet from the base. Find the angle of elevation. It's another tangent problem. We're just going to set it up the other way. So it's the tangent of some angle is equal to 51 over 68. So we're going to take the inverse tangent of 51 over 68. That's my angle. And that's going to give me, do some quick math in my head, or turn the page, whichever one, 36.9 degrees is my angle of elevation. And 16, tree is staked to the ground 20 feet from the base, so this is 20. The wire is tied 10 feet up. Find the angle of elevation. So once again, it's going to be tangent. Tangent of some angle is 10 over 20, or 1/2 to make our lives easier. So the angle is the inverse tangent of 1/2. For these, you want to make sure your calculator, both of these last two, 15 and 16, you want to make sure your calculator is in degrees. It doesn't make a lot of sense to find an angle of elevation that's in radians. Inverse tangent of 1/2 leaves us with 26.6 degrees. And that is it for the review for chapter 4.